It's a pleasure for us to have here Professor Ringwald. He is one of the leading experts in dark matter. That is another hot topic. And so please start.
So, thank you very much. Hello, everybody. So I will talk about axion dark matter. So I have to, could you please allow me to share the...
Yes, 1 moment. I have to make you co-author. 1 moment.
Make it small. Okay. So I was invited to give lectures on axions as dark matter candidates. And the plan of my lectures is the following. So now I have to, is the following. So I will start talking about the vacuum structure in quantum chromodynamics. And then I will talk about or lecture about the strong CP puzzle associated with this vacuum structure. Then in order to solve the strong CP puzzle, the axion was proposed or the axion comes in the course of solving the strong CP puzzle by means of the so-called Page-Wynn mechanism. And then after that, I come to that the axion does not to the lecture about the finding that the axion not only can solve the strong CP puzzle, but it is also a very well-motivated dark matter candidate. And finally, I will talk about axion experiments, because this is maybe the most interesting, also most interesting aspect is that nowadays there is a boom in axion experiments, and so this axion possibility as dark matter is very strongly tested in laboratory and also in astrophysical observations and so on. So today's plan is I want to talk about the vacuum structure in quantum chromodynamics and tell you what the strong CP puzzle is. So I start with the action of quantum chromodynamics of QCD. So QCD is an SO3 gauge theory with 6 flavors of quarks: up quarks, down quarks, strange quarks, charm quark, spot, and a bottom quark and a top quark in the fundamental representation of this SO3. So the most general gauge and Lorentz invariant renormalizable action for QCD is written here. So so this has been developed in the early 70s by Gross-Wilczek, Politzer, Fritsch, Gell-Mann, Leutwiler, and this extra term, which we were talking about this topological vacuum structure, was worked out by Bellamy et al., Toft, Kellen et al., and Chakib and Revy. Now let us go through the different terms here, step after step. So this first piece in the Lagrangian of quantum chromodynamics is the gauge covariant kinetic term. So it looks very similar to like the kinetic term in the U1 gauge theory of quantum electrodynamics. So it's built from gluonic field strength tensors. So these field strength tensors are written here. So they have not only this space-time indices mu, but they have also an internal color index, which goes from 1 to 8 in the adjoint representation of SO3. And so there is not only this antisymmetric part as one is familiar from the abelian gauge theory from quantum electrodynamics, but there is also a quadratic part in the fields involving this kind of structure constant. and here is the coupling constant of QCD GS. And this is so this gluonic field strength tensor is built from the gluonic gauge fields G mu A. So as written down here. So and of course, as we all know, this gauge covariant gauge kinetic term describes the gluons. So here, this is the part which describes the free gluons, and it describes also gluon interactions. So if you multiply this and sum of all these terms, there are terms which contain the triple gluon interactions and also quartic gluon interaction. And this is the new feature, so to say, of a non-abelian gauge theory in comparison to the U1 gauge theory of electrodynamics, which has no self-interactions of photons. Now, the next term here is the covariant quark-kinetic term. And so it involves the covariant derivative, so very similar as the covariant derivative in U1 gauge in the U1 gauge theory in electrodynamics. And so from this term, one gets describes quarks and their interactions with the gluons. So this gives the interaction with the gluons, of course. And here is also the parameters have a mass. So this is, so to say, the quark mass matrix. Now, so these kind of interactions, they are very well tested in hard processes and colliders and so on, and they also lead to the asymptotic freedom and all these nice features of quantum proper dynamics. And so they describe, so everything which can be described in perturbation theory is contained in these, so to say, in these two first two terms in this gauge covariant in this Lagrangian. What about the last term? So this last term was not there in the beginning in the development of Gross-Wilczek, Politzer, and Fritsch, Gell-Mann, Kleutwieler. They didn't have this term. What about this term? So what is the meaning of this term? I mean, it has dimension 4. So it's so the gluonic field strength tensors, they have dimension 2. 2 plus 2 are 4. So this is a relevant interaction. It's the most, and all this is the most general renormalizable action which one can write down in four dimension. Why did the founders of QCD, why didn't they write this term in addition? It's also a bit funny that there are these funny couplings there, but we will see why they are there, so to say, when we develop this. Now, so this is the so-called, this last term is the so-called theta term in the action of QCD. I call it now theta because we have multiplied this thing with the gauge coupling is dimensionless, and the theta is also dimensionless. It's just now at the moment it's just a parameter. We just write it down like that, so you don't know why. So but this I want to explain now why. So first of all, so this term, this chi dual, so it looks like the so to say from this point of view, this operator looks like the one which gave the kinetic term for gluons. However, it has a very important difference. So there is this tilde. This tilde means it's the field strength tensor contracted with this total antisymmetric tensor in 4-dimensional epsilon mu nu rho sigma. So this is the so-called Hodge dual of the gluonic field strength tensor. So it's not the field strength tensor, but it's just this combination of this projection, or so to say, of the gluonic field strength tensor. Now, and this makes this term very special, because this term, though the integrand in this term, so this g mu nu tilde, is a total derivative. So you can write this as a total derivative of a current of this current, where this current, I mean, you should put this epsilon mu nu alpha gamma, of course this is included in the current, where this current involves double and triple three gauge field or gauge field connections, so to say, or gauge fields. And so what does it, so, and this current is called the Chern-Simons current. So this theta term is essentially the four-dimensional integral of the diversion of the Chern-Simons current, which means then, of course, that this theta term does not contribute at the classical level, and even it does not contribute totally in perturbation theory, also a quantum mechanic in perturbation theory. So why is it that? So because this term depends only on the boundary information. So this term is essentially a topological term. It depends only on the boundary because it's a total derivative. So it does not contribute to the equations of motion and so on. So it doesn't contribute at the classical level, and it does not give rise to new vertices in Feynman rules. So, but why to bother then about this term? So if it doesn't appear in perturbation theory and also even not at classical level, why bother? But this was the finding of Galatov and the others, and this term is nevertheless important. It gives non-perturbative contribution in quantum theory because of the topological non-trivial vacuum structure of QCD. So so the vacuum in QCD is much more complicated and contains topological fluctuations, and therefore non-perturbative. It makes a contribution to the path integral, but from a non-perturbative contribution, and not one which one is seeing in perturbation theory. So to see this, we will use the Euclidean path integral representation of the vacuum to vacuum amplitude. So one can write the vacuum to vacuum amplitude in terms of an Euclidean path integral. Now, as you see here in the exponent, there is still something like the kinetic term we had before, and the quark covariant term. But this the kinetic term of the gauge kinetic term, now in this path in the Euclidean path integral representation, this is a positive term, and you have, so to say, a very nice behavior of this path integral, at least for the large field. So you have not these oscillating amplitudes, but you have a positive definite action from this point of view. However, there is this oscillating, this part keeps to be oscillating. This comes from the following fact. So if you start from the real-time path integral, where you have here, why this is always this e to the I d4x, where d4x is the real-time integral with the normal time, then everything is imaginary. But if you do this big rotation, you continue from you make an analytic continuation, and you continue the Minkowski time to the Euclidean time to minus I x4, and you continue the zero component of the gauge field with an I the fourth component in the Euclidean gauge field, you get this kind of transformation of the action, and notably here this chi dual term, this theta term, is obtained with still with an I here. This I remains. So such that, so to say that, so this is what happens if you do this continuation, then the Euclidean path integral factor, the path integral, this I integral d4x minus 1/4 chi dual plus chi plus theta chi dual goes to minus d4x 1/4 chi minus I theta this. So this is the first observation, and then the observation is, of course, so that then the next point is that finite Euclidean action, so that this action stays finite, which then requires that the classical gauge fields contributing to this path integral should be such that the field strength tensor vanishes when x goes to infinity. So all the Euclidean x goes to infinity. So only then is this, so to say, you have then a final Euclidean action, and things can contribute to this Euclidean path integral. But this means, that not that the gauge fields go to 0 at infinity, but this means that the gauge fields should approach a pure gauge form at infinity. So this chi mu should go to a pure gauge configuration. That means it has the form of a pure gauge transformation. A pure gauge transformation, a pure SO3 gauge transformation can be written as I over GS, a matrix UX from SO3 d mu u to the -1 for and so all the gauge fields which contribute make a finite contribution to this integral have to obey this boundary condition. Now, but if you have gauge fields for satisfying this boundary condition, now we can make more progress in order to evaluate this theta term. So we have this term now, this term gs squared over 32 pi squared chi twiddle. And I said, so this, it doesn't matter whether you are Euclidean space or Minkowski space. This can always be written as a total derivative. So here I write it as a total derivative of this Chern-Simons current. So this we had already before. But the point is then, now if you now evaluate this integral for the fields and the boundary, now you can insert the fields at the boundary, so to say, because this gives rise to a surface integral. But in the surface integral from the boundary, the only thing what remains is this second term, and this second term is essentially remaining like a u to the -1 u d mu u to the -1 u d gamma to the -1. And notably this factor of gs of gs squared or of here even gs to the cubed, they are cancelled by the factors 1 over gs cubed, which we get from these things. So this is essentially a pure number. It doesn't depend on the gauge coupling and so on. So this was the reason why we put this kind of normalization factor in front of it, just in order that this gives just a number, and this is indeed not even a real number, but it's really it's really element Z. So it's a natural number, and it is the so-called Pontryagin index of the gauge fields. So so in fact, so if you do this path integral, so to say, this factor gives just for each kind of configuration contributing, making a finite, having a finite Euclidean action. This gives just an integer number. Now, so I want to say a few more words to this integer number, or to this Pontryagin index or topological charge. So if you consider now a field, a group element in SO2, which is contained in SO3, then this each U in SO3 fulfilling this boundary condition, or provides a mapping from S3 at infinity to the S2 to SO2, which is also an S3. And such mappings from S3 to S3 can be associated a winding number. Like if you make mappings from S1 to S1, so which means from a circle to a circle, this you can characterize them by winding numbers, and this is the similar here for the SO2 case. So this Pontryagin index now in the case of U element SO2 counts the number of times the S3 at infinity is wrapped around the group manifold SO2. So it's really a topological number. So this Pontryagin index is also known as the binding number, and also known as a topological charge. So some people they give different expressions, but so if you hear a Pontryagin index, normally often they mean also binding number, or they say topological charge. So what does this mean? In Euclidean space, SO2 field configurations contributing to the vacuum-to-vacuum amplitude fall in homotopy classes of different topological charge. And it is not possible to continuously deform a field configuration into another of different winding number while maintaining the action finite. And moreover, general SO3 gauge field, because QCD is a SO3 gauge series, and now we have just considered this SO2, this winding number. General SO3 gauge field configurations can be classified in the same SO2 homotopy classes. The reason being that any mapping from S3 into a simple Lie group G can be deformed into a mapping to a SO2 subgroup of G in a continuous way. So hence there is no change of the homotopy class. So in general, so it means that also in SO3 everything can be in quantum dynamics. All the field configuration contributing to the vacuum-to-vacuum amplitude fall in homotopy classes of different topological charge. So this means the vacuum amplitude, which we have been written down before, can be written in terms of a Fourier series of Euclidean path integrals over gauge fields with fixed topological charge. So this ZQ is a Euclidean path integral where you fix which has a fixed topological charge. So all the fields at infinity, they go only to one-in-one or topological charge class, and you have this overall factor. So for each, you have to multiply each factor or each path integral with a fixed topological charge by the factor e to the I theta times the topological charge. So this is the thing which replaces the piece we had before. And you have to sum over, in order to get the vacuum amplitude, to sum over all topological sectors from -infinity to +infinity. And this is the so-called, this is the vacuum, this is the full expression. And this gives then also the theta dependence of the vacuum to vacuum amplitude in quantum chromodynamics. So, but what we learn also from that is, so before, so as I said, just to recapitulate, we had chosen to multiply this theta by gs squared over 32 pi squared. Why we did it? We did it because this object gs squared over 32 pi squared integral d for x chi whittle is an integer charge. So this is integer, and why had, for example, this gs squared, we can understand why this is integer, is because it has to cancel, so to say, the power, the inverse powers of gs from this gauge transformation in order to get a real number, not a real, to get a integer number, and so then, but then this means this theta, the remaining thing, the remaining parameter theta, this is really an angular parameter. So it goes from -pi to +pi. So there is nothing, so because then afterwards this is repeating itself. So it's theta is an angular parameter, and ordinary perturbative QCD, as we know it, resides in a topological trivial sector where Q is equal to 0. Yeah. Now we come to the next point. This is, or maybe so if people have some questions, we can. I can allow for one question if it's possible. Is it possible, Elena?
Yes, it is recommended.
Yeah. Okay.
Small break with the question for you, because very good.
Yeah.
So please, Camille, can you speak?
Hello. I have a question about this charge, topological charge.
Yeah.
So what is the topological charge of our vacuum?
No, the vacuum has no topology. So the vacuum, I mean, you are summing over all topological charges. So the vacuum, it's only, we have a topological trivial sector, but normally you have to sum over all the sectors, but there are correlation functions, which, for example, because this is just the vacuum amplitude. Yeah, for vacuum amplitude, you sum over everything. But however, if you now consider certain correlation functions, then sometimes these correlation functions obtain only the contribution from one topological charge sector. So this has to do also something with anomalies and such things. So if you have
but those sectors, they can like interact with each other.
I mean, only so transition from one sector to another sector can only happen non-perturbatively, so to say. So there is.
But that wouldn't require infinite energy. You said that.
Yeah. I mean, yeah, you have to tunnel somehow. Yeah, you have to tunnel between sectors, so to say. But this is, yeah. So you can, so in the vacuum, there can always, so you can imagine that the vacuum is something like there are these configurations they call instantons. So they can blob, but there could be also more general topological charge fluctuations, so to say. But they appear and disappear and so on. So the vacuum can be a complicated. Some people think about that the vacuum is like in QCD, it's like an instanton anti-instanton liquid or something like that. So I mean, in the vacuum there can be, but this is not. But all these things is then only modeling. But the fact that the vacuum you should take into account in general, for example, also in non-perturbable in lattice calculations, normally you should take into account this term. However, as we will see very shortly, this the theta. So to say, so in QCD, the theta parameter is really very small, and therefore, in principle, you can neglect it.
So only like the trivial sector is the biggest contribution, gives the biggest contribution.
Yeah, but the trivial it's the topological charge equal to 0 sector, but gives somehow, but it's still. There can still be a topological charge can also be happening of, so to say, if you have enough topological fluctuations with positive and with negative topological charge, so to say. It's not, you cannot say you can just ignore these things, but you cannot just say this theta is in fact small.
Okay, thanks for those questions. Let's give also to the other student a possibility if they want to give a question. Okay, if there are no any other questions, it is at your choice. Andreas, you can choose to have a 5-minute break or to continue.
Okay, then let's do 5 minutes break and then I continue.
Okay, very good. Thank you.
Okay, you're welcome. Now I want to talk about the theta dependence of the vacuum energy density in QCD, which is very important then for to understand how the axion can solve the strong CP puzzle. So, the good thing, so the vacuum to vacuum amplitude has a physical meaning, namely from the vacuum to vacuum amplitude, you can calculate the vacuum energy density. And so the vacuum energy density is epsilon 0, I call it epsilon 0, is related to the vacuum amplitude by this formula. So the vacuum to amplitude is equal to the limit of e to the minus epsilon 0 times the vacuum energy times the 4 volume, and you take the limit that the 4 volume goes to infinity. This comes essentially because this is a vacuum to vacuum amplitude. This is, so to say, the limit of e to the minus the energy times the time for time going to infinity. So therefore, and now we can use the fact, so to say, we write the vacuum to vacuum amplitude as a set of theta, and then from this relation above, we get the theta dependence of the vacuum energy from the logarithm of this partition function as a function of theta multiplied by 1 over the 4 volume, and we take the limit of the 4 volume going to infinity. And now, because this set for theta itself is a sum over, is so to say, a Fourier transform of these partition functions for fixed topological charge. We have here, so to say, that the vacuum energy is related somehow to a Fourier transform or the logarithm of a Fourier transform. And one important consequence from that is, of course, first of all, that the vacuum energy density is periodic in theta. So epsilon 0 of theta is equal to epsilon 0 theta plus 2 pi. So it has a periodicity, this vacuum energy. And secondly, the vacuum energy density has a minimum for vanishing theta. This comes, this has been pointed out by Waffer and Witten already in 84. This relies on the fact that the partition function for a fixed topological charge is positive definite for a vector-like theory as QCD, which implies then that Z of theta is always smaller than Z at 0, and this means that epsilon at 0 is smaller than epsilon at theta. This is important later on then for axion physics, because as we will see, the axion field will correspond to a space-time dependent theta parameter. So the axion field essentially is a theta of x, and the field dependence of the axion potential is then given by the theta dependence of the vacuum energy density. So this epsilon of theta is essentially the potential, energy, or so to say, of the axion, and in particular, this result implies then that the axion has a vanishing vacuum expectation value, because the minimum of this epsilon theta is at 0, at theta equal to 0, and this is the important fact to solve the strong CP problem. Now, further progress, so one can even learn more about this vacuum energy density, how it depends on theta. Now we have just learned that it has it's periodic, it's a periodic function, and it has a minimum at theta equal to 0. Now, but further progress can be made in the chiral limit. So if the quark mass, or all these entries in the quark mass matrix, so to say, go to 0. To see this, we consider first, so how can this be related to the theta? Because we thought M the mass matrix, or the quark masses had nothing to do with theta, but as we will see, it has something to do. So to see this, we just first start with the, of course, very unrealistic case of just one light flavor, and so it's just we think that we have that QCD is such that there's only one light flavor, just called U, the up quark, so to say. Now we can exploit the chiral anomaly. The chiral anomaly says that the fermionic measure in the path integral, so this integral dq bar, which we have seen, is not invariant under chiral transformation. So classically, this is an invariance of the action of QCD, or for this one flavor QED. If I make such a, if I do such a chiral transformation, I transform the quark field, the up quark field, by e to the I gamma 5 alpha times q, then the action remains invariant, and I would think that this chiral current is conserved. However, in fact, if one does this carefully, so for example, Fujikawa has proven that the measure, the fermionic measure in the path integral, this dq bar, if you do such a transformation, transforms, and the transformation in the transformation formula you see here, there appears the topological charge. So what means, but this means, so to say, one may trade the theta parameter in QCD for a phase of the quark mass. So in this case, you can trade it for a phase of a quark mass, and in particular, this means, of course, then the vacuum to vacuum amplitude and thus the energy density depends in this one flavor QCD only through the product. So the mu times e to the I theta. So the vacuum energy will be only just a function of mu times e to the I theta. Now you can evaluate this further. Since the spectrum of the theory does not contain massless particles in the chiral limit, so unlike in QCD, you have at least two flavors are essentially have a mass much less than the confinement scale in QCD, and therefore, so to say, one has in two flavor QCD, one has the pions as Goldstone bosons as the lightest nearly massless particles. But here in this theory does not contain massless particles in the chiral limit. Therefore, the expansion in powers of mass, if you expand this epsilon of theta in powers of mass, does not give rise to infrared divergency. Then this means that it's an ordinary Taylor expansion, so you can expand this, and for a small mass, and what you get from that, you get, so to say, that the first non-trivial term in theta will just be given, will just be proportional to cosine theta and to the mass of the quark, of the up quark mass, and this constant is given in terms of the quark chiral condensate in the theory. And you see, in fact, so this, as promised, this vacuum energy has an absolute minimum at vanishing theta angle. For theta equal to 0, it has the minimum. And and this is true, so to say, as long as in this expansion for small quark masses. And moreover, the vacuum energy is independent of theta if the quark mass is 0. So this is also something which one has to remind, which also follows from this general thing. So you have two things: vacuum energy has absolute minimum at vanishing theta angle, and moreover, in this one flavor theory, the theta dependence is very, so the periodicity function is very simple. It's just a cosine of theta. This is different in the more realistic case of two light flavors, say U and D. If you have two light flavors, again, you can exploit the chiral anomaly. Now for two light flavors, you can make a common chiral transformation of this field and to trade the theta parameter for an overall phase of the quark mass. The vacuum amplitude will now depend on a theta parameter only through this product. But in this case, the spectrum of the theory does contain massless particles in the chiral limit, namely 3 pseudoscalar number Goldstone bosons, the pions, pi plus, pi minus, pi 0, originating from the spontaneous breaking of the chiral symmetry by light quarks. And so, but still, then you can use the effective theory. You can now calculate the vacuum to vacuum amplitude for realistic QCD at large 4 volume and small quark masses. You can compute using the effective field theory of pions, because these are now the relevant degrees of freedom for this. So near the QCD, near the so to say in the infrared. And then you can exploit this chiral effective field theory you treat, so to say, in the chiral effective, in this chiral Lagrangian, you absorb the theta parameter of QCD in the quark masses, in the quark mass matrix, so to say, and then you just calculate the vacuum energy in this theory, and you obtain this result. So instead of a cosine of theta, you get here a much more complicated result. So again, it's periodic in the it's periodic in theta, and the epsilon minimum is at theta equal to 0. And again, also if one of the quarks has a zero mass, so say the m up, then you get that there is no dependence on theta at all, and so all these limits are fulfilled, and so you see, instead of this orange curve, which you would have gotten for a theory which has just the cosine potential, this would have been the one flavor theory. You get a more enhanced thing at the values of pi, so to say. But so this is the theta dependence of the vacuum energy density in QCD. It looks like that, and so this already gives you an idea. If this will be the self interaction potential of the axion later. So this is determined by the, so to say, by the low energy effective field theory of QCD. So to say, the self interaction of the axions are determined by QCD, and so they look like this. In particular, you can then read off the axion mass by taking the second derivative of this function at 0. This will give the axion mass, and you see the axion mass will be related to the mass to the mass of the pions and to the ratio of the up to the down quark mass. Now, so far, so this is the so now we know, so to say, the function, so the theta dependence of the vacuum energy into QCD. Now the question is, of course, still we cannot how can we measure this? The question is, how can we measure this theta parameter? So how large is this theta parameter? So this is an additional parameter as to QCD now. So normally, so in the ultraviolet, QCD has two parameters, as the gauge coupling and the quark masses as parameters. And now we have found out that there is one additional parameter. This is the theta parameter, but we have no idea at the moment how large this theta parameter is and how it can be. How can it be measured? Now, so I will come to the point that arguably the best way to measure this theta parameter is by measuring the neutron electric dipole moment. No, but before we go to that, so first of all, we have to see what is theta, the theta term doing. So in fact, the theta term violates both time reversal invariance and parity, and thus, because of CPT, it violates CP, charge conjugation and parity. Now, how can we see this? So this can be understood now by expressing this theta term, so this chi-chi dual, in terms of color electric and color magnetic fields. And if you do this, if you introduce color electric, so in analogy to electrodynamics, you introduce color electric and color magnetic fields. And of course, these fields in themselves, they are not gauge invariant, but this combination, of course, is gauge invariant at the end. So they have still color indices A and A, but it looks like this term is essentially an E dot B interaction, quote unquote. So it has the color electric dotted into the color magnetic field. Now, what are the properties of this under T and P? Now, it's well known that electric fields are even under T. So if you replace time by negative time, then they are even, and they are odd under P. While magnetic fields are odd under T and even under P. So, and electric fields are odd under C, with the consequence that they are even under CP, because we said that they are also odd under P. So electric fields are even under CP, and magnetic fields are odd under C, with the consequence that they are odd under CP. So which means then so this E dot B is odd under CP. So and the most sensitive probe of T and P violation in flavor conserving interaction is in fact the electric dipole moment of the neutron. Now the electric dipole moment of the neutron corresponds to this effective electric dipole interaction. So you have here the fields for the fermionic fields for the nuclei spinors. Then you have the F mu for electromagnetism, and this corresponds to an effective dipole interaction. So this dN can be split. So first of all, this must involve a factor of E for the electric charge, for the electric dipole moment, and it should be for small theta, it should be proportional to theta. So it has 1 power in theta. And now the question is, how large is this coefficient, this dimensionless, this coefficient, which is not E and theta are dimensionless. This is a dimension 5 operator. This has 3 half dimension, mass dimensions 3 half, so it's 3 plus 2 is 5. So this should have a dimension 1 over mass. Now, but in fact, there should be, because this, so naively one would say that this Cn should be just proportional to 1 over the nucleon mass, and then so then this parameter should be of the order of 10 to the 1 over the nucleon mass is Fermi, so it should be 10 to the minus 13 E centimeter, so to say 10 to the minus 13 E centimeter times theta. However, because we have, because we had already said that if one of the quark masses would be 0, so then the effect of a theta parameter would be 0 because of the chiral anomaly and these consequences. Therefore, this coefficient should vanish if one of the quark masses is 0. So it should be proportional to, so to say, to the reduced quark mass, which is mu times md divided by mu plus md. And so we get from dimensional grounds, we get now, so to say, a suppression factor, so to say. It's not 1 over mn, but it's 1 over it's not 1 over mn, but it's 1 over mn squared, because the other power comes from the dimensional ratio of the reduced quark mass divided by the nucleon mass. And because the quark masses are only in the mega electron volt range, we get a further suppression by about 3 orders of magnitude in comparison to the naive power counting just 1 over the nucleon mass. But this power counting takes into account the chiral anomaly. Now, but this would be then the educated guess. And in fact, the currently best theoretical determination of this coefficient was done by Pospelov and Ritz. They use QCD sum rules. So note, of course, you have to use non-perturbative methods to calculate this coefficient. And the lattice is at the moment has difficulties to approach this quantity because of the sign problem, because E of I theta has alternating signs, so to say, and therefore typically one has to use other methods. So you see this has a more than 30% estimated error, but still it's supposed to be non-zero, of course, and it's of the order of 10 to the minus 16 centimeter, as we had already guessed here. So but however, the experiment now, for example, from PSI, the neutron electric dipole moment experiment found an upper bound on the electric dipole moment of the neutron of the order of 2 times 10 to the minus 26 e centimeter. So this is a mismatch from the expectation to this, a mismatch of 10 orders of magnitude, which means that this theta absolute value should be less than 10 to the minus 10. And this is the strong CP puzzle. The puzzle is not only it's a puzzle, but because even if you arrange that it is topological, so to say, that the topological theta angle is very small, but in fact, so this theta, the physical theta parameter is something like is given by the topological or theta parameter and plus the quark plus the phase of the overall phase of the quark mass matrix, and which has nothing to do with this other parameter, and they should be cancel each other in such a way that it's less than 10 to the minus 10. So this is really a puzzle. The thing is, of course, you can also not solve this puzzle by anthropic reasoning, because there you could try to calculate other things, or people have also calculated other observable quantities which are not as sensitive as the electric dipole moment, but other quantities, how they would change for non-zero theta from using chiral perturbation theory and so on. But there one could say that anthropic reasoning can help you maybe to explain that theta should be less than 10 to the minus 3 or so, but 10 to the minus 10 is out of the question. On the other hand, of course, we can also nothing spectacular happens, but this has nevertheless this is such a puzzle that people have thought about solutions, and we will very soon now come to the axionic solution of this puzzle. But let me now again ask now about questions on what you heard until now. So I invite now again for questions.
So, do you have any question?
Can I make a question?
Yes, Alessandro, please speak.
What I didn't understand is why the fact that the theta parameter is so small,
Yeah,
it's a problem.
it's not a problem. It's a puzzle.
Why?
It's not I call it a puzzle. Yeah, because I mean it's such a small parameter, and in principle, this theta. So as I explained before, you can change this theta. So some people call this theta bar. So the physical theta parameter is something which contains, so to say, the theta from the topological structure in QCD plus the overall phase of the quark mass matrix. And these two things together, they cancel each other in such a way that at the end only 10 to the minus 10 remains. So
it's like a fine tuning, almost perfect cancellation.
Yeah, it's almost perfect cancellation between a thing which comes from this SO3 gauge theory and the others from the quark mass matrix.
Because you can relate this theta parameter to the quark masses.
Yeah. I mean, so this is was the way also what we used, so to say, to calculate the theta dependence of the vacuum. In this case, you absorb, so to say, all the theta which is there in the quark mass and in the quark masses, and then you could use chiral perturbation theory to calculate this potential. So you can, so sometimes it's better to have everything in the, so to say, outside the quark mass matrix, and sometimes it's better to have it inside. So it depends, yeah. But at the end, so the question is, at the end, why is there this perfect cancellation?
Thank you very much.
Yeah.
Any other question? Please, thanks for this question.
Hello.
Hello?
Hello? Yeah.
Yes. Can I make one question?
Mm-hmm.
Okay, can you tell your name?
Yeah, Abhijit.
Okay.
Abhijit. Okay.
Abhijit, we have already familiar with CP violation in kaon sector, like in weak interaction.
Yeah.
So can you compare or explain why it's not a strong CP violation instead of a strong CP puzzle, a comparison, how they are different?
So so to say, the CP violation, while the normal CP violation arises from non-diagonal flavor interactions, and here this strong CP violation is a violation in the diagonal flavor interaction. So there is only, so this is very different, so to say, phenomenologically.
Okay.
So
You have explained very well. You have explained really very well. Thank you.
Yeah.
Thank you. Thank you.
Any other question? Okay, if there are not any other questions, you can continue, please.
Yes, okay. So then I continue. I came through much wider as I thought, but that's good because then people have not forgotten what I have said before. So now I come to the axion. So the axion solution of this strong CP puzzle. So now, wrong thing. So the axion. So the idea of the axionic solution of the strong CP puzzle is very simple in a sense. So the idea is to promote the theta parameter to a dynamical field. So until now it was just a parameter, so it was the same everywhere, so to say. But now we want to promote it to a dynamical field. So the idea is to add to the standard model a Nambu-Goldstall field. So it's, so to say, a field which is like a whose fundamental range is just like an angle. So it's a field, a dimension 1 field A of x divided by a dimensional full constant of mass dimension 1. And this thing should have a range between minus pi and pi. So Fa should be essentially the periodicity of this field A of X. And this Goldstone's field should respect, apart from an effective interaction with the gluonic topological charge density. So we require that this field couples linearly with this topological charge density. So it should be alpha x times alpha s over 8 pi, which was before I always wrote gs squared over 32 pi squared, but this is because alpha s is g squared over 4 pi, g mu tilde. So this require that this new field which we have introduced, that this has such a linear interaction with this gluonic topological charge densities. And apart from that, it should realize a non-linearly U1 Peccei-Quinn symmetry. That means its action should be shift invariant. So if you add to theta a constant, then the action should be invariant. So this is the only term which violates this, so to say, this shift symmetry. So in a sense, so you see already, so we require just that this theta, that this is, so to say, a space-time dependent theta term. So now, of course, no, Janu had in analogy to pion physics, this Fa is dubbed, or it's called a decay constant. So it's then later it's called the Axion decay constant. And so to say, so we said this is a nonlinear realized U1 Peccei-Quinn symmetry. So the Fa will be of the order of the breaking scale of a global U1 Peccei-Quinn symmetry, and this would be the Goldstone boson field of the breaking of this global U1 Peccei-Quinn symmetry. So, but at the moment we just need the low energy effective field theory of this Nambu-Goldstone field, and this low energy effective field theory is given just by the kinetic term of this theta term and by this interaction theta of x alpha s over chi times chi dual. Now, of course, this is a dimension 5 interaction now of this field of this field theta. So this theory will break down at the scales of order Fa, and then above that it will need a UV completion at scales above this scale. But at the moment we don't care about that. We just think this Fa should be much larger than the QCD scale, then everything is fine. Should be much larger than GeV scale. Then at the moment we don't care much more about that, apart from that. So now exploiting this shift symmetry and this effective interaction allows us to eliminate the QCD theta bar parameter by the shift. So now we have assumed that that we have removed, we have put all the terms now coming also from the phases of from the overall phase of the Gorg mass matrix. Everything shifted, so to say, in this chi dual term in QCD, and in front we have this theta bar. But now we can of course shift our field theta of x by a theta bar, and then so at the end, of course, at the beginning, of course, we start with this is the QCD part, and this is the new part of this new field theta, and now we make this. Now we do this shift, and during the shift we have absorbed completely this theta bar. The theta bar is no more there, so there is only a theta, the theta of x. So now this Nambu-Goldstone field has eaten, so to say, this theta bar. Of course, there will still be a neutrino electric dipole moment will now be induced by this theta of x. And but this QCD theta parameter is promoted to a dynamical field. So this was the way how to promote the QCD theta parameter to a dynamical field. And later on, tomorrow, so we will see then models which are UV completions of this model, which yield then explicitly this term, but there is no doubt that such models will exist. So to say, it's just we at the moment we just consider this low energy effective Lagrangian, and it's easy to write down this kind of term, and to introduce this such a Nambu-Goldstone field with this shift symmetry, and in this way we have eliminated the QCD theta parameter. So it's swallowed now. So now let's then consider the dynamics of this theta of x at energies below Fa but above lambda QCD, and this will be described just by the kinetic term of this field. The kinetic term will have this Fa squared. This is the as I said, the decay constant, and then here is this theta of x alpha s chi dual term, and this has absorbed, so to say, the theta bar is now absorbed by this thing. And now I will describe how this so-called Peccei-Quinn mechanism solves the strong CP problem. Now, as I said before, now we have this theta of x, but we can integrate out the gluons, so to say, by matching this theory to the effective field theory at low energies, where we have, of course, now in addition to the pions, we have now also this Goldstone boson. But the potential, the self-interaction potential of this Goldstone boson will coincide with the vacuum energy, with the theta dependence of the vacuum energy QCD. So this is clear. So we have this kind of potential. So in particular, now we can of course the question whether CP is violated by this theory is now the question. Whether this potential, the vacuum, so to say, that the vacuum of this potential has so to say, favors vacuum expectation value of theta equal to 0. But this is guaranteed because I said, okay, now it has a minimum at 0, which means that there is no, in the vacuum, there is no strong CP violation. So the vacuum expectation value of this newly introduced theta field is 0. So, and then of course, and this was, so to say, this was the Peccei-Quinn mechanism. Peccei-Quinn, if you read the papers, it's much more complicated, but in principle, this is the condensed. This is the idea, but it was not realized by Peccei and Quinn. It was not realized that their mechanism predicts also a pseudo Nambu-Goldstone boson, because you have this, because this is a dynamical field, of course, and this has, you can read off the mass from the second derivative at 0 of this thing, and so there is a particle excitation of the field A, and this was dubbed the axion by Frank Wilczek. So because he said, he calls it an axion because it cleans up a problem associated with an axial or chiral current in QCD, and this axion is a cleansing detergent which you can buy in US. So nowadays I saw only in other countries. I don't know whether it's still produced also in US, but I have a pot of Axion detergent made in I think in Chile or so. So I mean, there are still, so you can buy it at in some countries. So and this was the reason why it's called Axion. And it's maybe it's similar like with the Higgs mechanism. It was important that there was and I think in the original paper of Higgs, Peter Higgs, about the Higgs mechanism, he didn't mention the particle, but in the published version he mentioned the Higgs boson. But here it's also similar to Roberto Pecce and Helen Wynn. They didn't mention the axion or this particle, but later on, then Weinberg and Wilczek, they pointed out there should be also a particle, and maybe you can search for this particle, so to say, because it mixes with the pions and has inherits some interactions and so on. In principle, one can look for it. And the nice thing, so if you do it like that, so it has a model. So the Axion has a model independent prediction of the mass. The mass is determined by the second derivative of the effective potential, and it's given, so to say, by something like a seesaw between the scale of chiral symmetry breaking and the scale of Pecce-Quinn symmetry breaking. And in the original model of Pecce and Quinn, so they had a certain UV completion of this Axion model in mind with a 2 Higgs doublet model. This FA was of the order of the electroweak scale. However, this kind of Axion is nowadays, as we will see later, completely excluded. So this FA has to be really large, order of 10 to the 10 GeV or so, in order that the Axion is viable, is a viable BSM particle, because otherwise it's excluded by beam dumps and astrophysics and so on. So as I said, so it's parametrically suppressed by the decay constant. But if you plug in the values for these Borg mass ratios and the pion mass and the pion decay constant, you get that the Axion is a very light particle if the decay constant is large. So if the decay constant is of the order of 10 to the 9 GeV, the Axion has just a milli-electron volt mass. And I said it reminds, so this relation reminds on a seesaw mechanism. So it's the larger this decay constant, the smaller the mass. And also the larger this decay constant here is, the smaller the interactions with the standard model, as we will see then later, I guess tomorrow. So of course there are now, meanwhile, there are really precise calculations of this by including order alpha QED corrections and next to leading order corrections in chiral perturbation theory. And this is the most recent result by Gorgetto and Villadoro et al. So, it's like this number, but this mass is very much determined, which means, on the other hand, if there are some other ways, so if there are ways to determine this mass, and as we will see then later in this in the lecture, if one determines the Axion dark matter mass, mostly because in these Axion dark matter experiments, you can determine the Axion mass probably up to with a relative uncertainty of 10 to the minus 6, which would mean then you can determine this FA to a very high degree of to very high precision in a sense. But this is still to be seen. And I think this is how far I wanted to come today. Now there are a lot of we have still a lot of time to question. I could still continue with, and maybe I continue with one thing. So which is also completely model independent. So this is model independent as long as we stick to what I said. as we say, the only so as long this is the only term, so to say, which violates the shift symmetry. It's just this contribution. If there can be further terms, you can change this this mass formula. However, of course, you should. So I mean, it's not very easy to do it without tremendous fine-tuning. So there are ways to do that, and we have also Anson Hook has found a very nice thing, and I also worked with Pablo Guedes and Belengavela and others, and Luca Di Lucio on this kind of thing. So one can so to say, there are certain models, but there are I guess only very few which give a natural generalization where you can violate, so to say, this more or less model independent relation between the axion mass and the axion decay constant, which is just given by chiral perturbation theory. So there is another relation which is more or less also fixed, and this is the coupling of the axion to the nucleon electric dipole moment. Because of course now, as I said, we have introduced the axion as a space-time dependent theta parameter, which would mean, of course, that the axion has a model independent coupling to the EDM of the nucleon. So it will be, so instead of before we had this dn, which was given by Cn ADM E times theta. And now we just replace this. We have now replaced this just by the axion field. So it will be linear in axion. And this Ga and gamma is predicted to be given by E times the Cn EDM, which we have seen before, and which has been calculated by Pospelov, divided by Fa. So this is also a model independent prediction, and if you take this prediction and you take the prediction of the mass of the axion, which, as I said, goes like 1 over Fa, and just remember here, goes like 1 over Fa, and has this kind of form. If you do this, then of course, then you find that this coupling, that this axion EDM coupling is proportional to the mass, because the mass goes like 1 over Fa, is proportional to the mass, and it has a very, so for all kind of axion models, it has a very small error bar. And the only exception is if you find something, if you find an extra contribution which violates the shift symmetry, which is canceling the leading contribution for QCD, then maybe you can go away from this line. But these are the typical models which are on the market don't do that. They start always with the only violation of the shift symmetry by this Chi dual term, and this is normally called the poor or conventional or canonical QCD axion. And in this parameter space, it lies on a very thin line, and the thin line is just the theoretical prediction. But any axion model, so we will later hear about KSVZ axion, DFSZ axion, or GATT axion, or any, name it, will always live on this very low line. And there are only a few exceptional models where you have either fine-tuning or a very new symmetry, like the ZN axion model of Anson Hook, which we have worked on, which can populate also this parameter space above. So, but this coupling, so as we will see in the last section, so of course the couplings of the axion to standard model particles are the ways how to test the model. And for example, this axion nucleon, this axion EDM coupling is phenomenologically very important for experiments searching for axion dark matter via oscillating nucleon electric dipole moments such as NEDM and Caspar electric, which are here, have already produced some limits from the non-observation of such oscillating nucleon electric dipole moments due to axion dark matter. So I make a stop here and invite for questions.
So any question? Apparently no question.
Okay. And in principle, I can also continue. Should I continue, or what do you think?
I think that you can continue for other 10 minutes and then you stop and you ask a question.
Okay, yes, okay, good. So as I said, so we start with the vanilla. So the thing what we are considering at the moment are the consequences of this very simple Lagrangian. This is the so-called, we are looking for a low energy effective theory of consequences from this Lagrangian. And so we already said, so we derived the axion mass. We derived the axion coupling to the electric dipole moment, to the neutron, or the effective coupling of the axion to the electric dipole moment, and now we are. So there's the third consequence of that is, of course, now because the axion, as introduced here, of course, mixes with the pions, and through the mixing with the pions, there will be also, because the pions have interactions, the neutral pion has interactions with two photons or with FF dual, then also the axion will inherit such interactions, and this is this so-called coupling to the photon. Also from the mixing with the pion, the axion will inherit at energy scales below the QCD scales also a model independent contribution to its coupling with two photons. So this comes originally from the Chi-Chi dual interaction, but the Chi-Chi dual interaction we have now absorbed, so to say, into the effective Lagrangian. Chiral effective Lagrangian, which now describes not only the pions but also the axion, and from this mixing one can calculate the so to say the interaction of this of the axion with two photons or with FF dual, and in fact, so normally this is parameterized by 1/4 GA gamma, where GA gamma is an MI, I mean model independent, where GA gamma is the coupling to the coupling to the photon, the coupling parameter, which has of course dimension, because this has dimension 5. 2 plus 2, yes, 4 plus the axion 5. Dimension 5, so this has again dimension of 1 over the mass, so it should be 1 over FA, and it's typically, so one takes out this parameter alpha over 2 pi, because this is similar to the combination which is before which is in front of the Chi-Chi dual term, and of the interaction with gluons. Of the axion, and yeah, and then this CA gamma is then, so this alpha is the electromagnetic fine structure constant instead of alpha S, which we had before, and this CA gamma is now a dimensionless constant of order unity, and in fact from leading order chiral perturbation theory, one calculate the Ca gamma, the model independent contribution from this from the Chi dual term, and it's related to the ratio of the up to the down quark masses by this factor. And if you take this, so the ratio of up to down is of the order of 1/2. So if you take this, then this model independent distribution will be of the order of minus 2. And this has been calculated to next to leading order using chiral perturbation theory, and it comes then out as minus 1.92 with an error bar of 4. So this coupling, the coupling to photons, will be very important because most of the experiments nowadays to search for the axion will be dependent, are looking for the interaction of axion with photons. So this is so to say the landscape of this kind of experiments. We will talk later in the third lecture about this. So what is plotted here is this Ga gamma. Here it's called Ga gamma gamma, but so it's this kind of coupling. It's the same coupling, a little bit other notation, versus the axion mass. And typically, so this so-called hadronic axion, which has only this Chi dual interaction coming from the ultraviolet, is equivalent or is the same as the prediction of the KSVZ. It's essentially the SKSVZ model. And so this is the prediction of the KSVZ axion. And here are limits which are coming from stars and so on. They're coming from light shining through a wall and from axion dark matter experiments. And we will learn very much about this in the coming lectures. But already from this, one can see that the axion mass, so at least the axions living on this line, for example, they have an upper bound on the axion mass from astrophysics that they should be have a mass less than an electron volt or so, something like that, and so on. So I think okay, then I stop here. And
so let's thank the speaker. If there are further questions. Okay, Matteo, please.
Can you hear me?
Yes, well.
Thank you very much for your very nice lecture, first of all. Yeah, my question is about the corrections that you introduced in the determination of the mass of the action. You talk about alpha correction and next to leading order corrections.
Yeah.
But are there any others?
I mean, because in principle, I mean, one could do higher order, but it seems that this perturbation theory, which you are doing, converges nicely. So I think one can rely already on the error bars. So I think there's no point to calculate higher order corrections to these things.
Okay. Thank you very much.
Yeah, you're welcome.
Any other question? Okay, so if there are not any other questions, we thank the speaker and that we will see again tomorrow. Okay?
Okay.
So, bye-bye.
Thank you. Goodbye.